Hi guys, this is Fazan and welcome to today's session on divide and conquer algorithms by great learning. So before I start, can you guys quickly confirm if I'm audible? Is everything okay? Can you see me? Can you see the slide deck? Can you see this pointer? If yes, just then write a quick confirmation in the chat. Just write a yes. Quickly guys, just confirm. Write a yes. In the meanwhile, okay, great. So in the meanwhile, let me give you a quick tour of how our academy looks like. So open in any browser, type in Great Learning Academy. Therein, just click on this first link, which is free online courses with certificates in India, Great Learning, right? Click on it and it will redirect you to our academy. Therein, you can easily see these are the advanced PG courses that we have. Just click on it and open it. Okay. There you have some popular courses: data science, AI, machine learning, data science and engineering. These are all our PG courses, right? And we have courses on AI and machine learning, cloud computing, cyber security, software development. And if you have any confusion, we have a number given over here, right? You see 08047177774. You can just give us a call and we will see what we can do. Okay, cool. So these are all our PG courses. These are the live sessions that are upcoming live sessions. Right now I'm taking this live session on divide and conquer algorithms. Tomorrow Aniruddha is taking data science for beginners, and Ritvik is taking Java Ops concepts in Hindi. So as you can see, we have live sessions both in Hindi as well as in English. So this live session currently which I'm taking is in English. Okay. So apart from that, we have some courses. These are our popular courses. We have courses in IT and software as well. We have data structures and algorithms in Java, Java programming, cyber security, ethical hacking. All these are courses available, and these courses are for free. Okay. We also have courses in Hindi. That means you can learn in your preference or language preference, whatever the preference you have, you can learn in that language. Okay. So we have R programming, AWS, digital marketing, data science, JavaScript, Linux, right? Tableau is there, HTML is there, CSS, Splunk, Bootstrap. All these courses are available for free. And in order to get the certificate, you have to answer 6 questions correctly out of. Is everything totally for free? Yes, the courses which I was just showing in the IT and software and all the fields that are there, those courses are for free, and you also get a certificate which you can easily add, the completion certificate, which you can easly add into your resumes and LinkedIn profiles, and also add the projects which you do during those courses. Okay, cool. Our PG courses are paid courses. Okay, and we also have a YouTube channel. If you haven't subscribed, we have a ton of data on that as well. We have lectures which are more than 10 hours. Content is there on JavaScript, data structures and algorithms in C. We have recently we uploaded a video on data science, right? So all these courses are available on our, yes, on our YouTube channel, absolutely free. Okay, so you just have to subscribe to the channel and that's it. Okay, cool. So now let's get started with this session of ours, right? So if I'm looking on this side, that means I'm looking at your chat, guys, so don't worry. Okay, cool. Okay, I can see some yeses. Okay, so now let's start. So what are the things that we are going to cover in this session? So first we are going to talk about the algorithms. What is an algorithm, right? Cloud computing, yes, you have to check. Okay, so we will be covering algorithms. What is it and what is the algorithm analysis? Okay, then we will talk about binary search algorithm, which is one of the algorithms which follows DNC, right? That is divide and conquer paradigm. It is one of the algorithms. Then we'll talk about quick sort, and then we'll talk about merge sort. These are the simplest algorithms, right? These are the simplest yet most widely used algorithms, right? Most widely used algorithms which follow this paradigm, that is DNC, divide and conquer. Okay, cool. So now let's start. So first we are going to talk about what is an algorithm. So algorithm is nothing but a step-by-step approach to solve a particular problem. Let's suppose you have a problem and you want to find the solution of it. What is the first thing that you do? You write the algorithm and then you try to figure out, okay, is this the best that I can do? If yes, then you go and code it out. Okay, you write the pseudo code and then you write the program in your desired language. Right now, this algorithm should be easily understood by a non-technical person. Okay, the one who is not having any idea of any programming language. Okay, no programming language. Okay, so it doesn't have any idea. This algorithm should be written in such a manner that it should be understood by this guy, okay, who is a non-technical guy. It is free of programming constructs. That means it is not dependent on, okay, you are writing an algorithm in C or C++ or Java or Python. Okay, no, that's not. So algorithm, now this is the case when your algorithm looks almost correct, right? And if it is not, then you go ahead and optimize it rather than going in and coding it out and then optimizing it. This is a very costly operation, right? In order to do, or you can also optimize while you are performing, or while you are writing this algorithm, you can optimize it at that time. Okay, so it gives you a crisp solution. There can be multiple possible algorithms of a given problem. Obviously, now I'm writing some algorithm and then I'm changing it, right? So, or if I'm writing some algorithms to let's suppose swapping a number, I can use a temporary variable and then swap a numbers, wherein you can just use you cannot you might think of an algorithm in which you are not using any extra variable, right? This temporary variable, you can think of that, which we can do, right? So algorithms might be different from one algorithm can be different from the other, and that both these algorithms will be of the same problem. That means one problem can have multiple algorithms. Okay, one obviously efficient than the other, and that can be the case. Okay, so this is what is an algorithm. Okay, now what is the next thing? Then it is algorithmic analysis. Then how you will analyze, is this algorithm the correct algorithm? Is this correct? How can you analyze your algorithm? So again, that can be done what? With the help of finding or trading off between time and space. So always whenever you write an algorithm, you do a trade-off, right? Is this algorithm you want to save your time, you want to make it time efficient, or you want to make it space efficient? So there is always a trade-off between this time and space requirement of your algorithm, right? And is this thing helps us to find the optimal algorithm. Okay, based on these factors, the time and the space, you can easily analyze, okay, is this algorithm the right algorithm? Is this algorithm is the one that is very time efficient? Okay, now let's suppose you're building an algorithm or you're writing an algorithm which takes big O of n square time. Okay, I will explain what are these big O terms and all these things. But the space required is constant. But now I told you, okay, you can use any extra space. That means I'm doing here what I'm doing a trade-off between time and space. Okay, so I'm saying that, okay, what Nisar, okay, Nisar, do one thing, take extra memory, but I want to optimize this in terms of time. So what Nisar did, he went on and used big O of n. That means he increased his space complexity and he reduced his time to big O of n, or even much better, big O of log n. Okay, so now this, you see what I did here, I did a trade-off between time and space. Either I can make it space efficient, or I can make it time efficient, or in some cases it can be both, right? Time and space efficient. Okay, so okay, so what are the different types of algorithmic analysis? So you always have a best case for a given algorithm, you always have a average case, and we always have a worst case. So we will talk about these average cases is moreover close to the worst case, because it is something that is half of what the worst case is. Okay, but we don't take here into the consideration the constants and the smaller terms that are there. So we don't really talk about this average case, but you should know. Okay, so we talk about best cases and we talk about worst cases. Okay, so what is the use of time? So the time is something that you can deduce something. Okay, let's suppose you wrote an algorithm and now you want to check how much time does it take, to execute or to run, how many iterations do I require. Okay, so it can be a number of unit operations that you perform. Okay, Aditya, so it depends, right? So now let's suppose you have an algorithm, right? Let's talk about the searching algorithm. Okay, so you have an algorithm and now what you are trying to do, you're trying to find 10. in your algorithm, you're trying to search an element which is 10. Now you're applying a linear search. Okay, now what is the best case of this? That means you're trying to search in 10, that is this element 10, and it will be present in the first location and you will not check any further. You will break out of the loop, and there you have it. This is your best case, right? That it performed, you only performed a single unit of operation, that is constant time operation was performed, and you were able to find this element that you were trying to search, okay, in a constant amount of time. So this is your best case. Now what about the worst case? Okay, so worst case is you're trying to find this number which is 50, or even further. If you go any further, let's suppose you're trying to find 60. Now you check, is this number 60, is this number 60, is this number 60, is this number 60, is this number 60? You are at the end of the array, right? So the number of iterations that you did was equal to the number of items that were present in this array, that is n. Okay, depending on this, the worst case is of this searching algorithm, the linear search, is big O of n. Because now whenever you talk about time complexity, you always talk about worst case. Now why? Can anyone tell me why? Quickly. Quickly, guys. Just write it in the chat. Now, why do you always talk about what? Worst case scenario whenever you're talking about time complexity or even space complexity? Okay, I cannot see any comments or anything in the chat section, so let me just clarify it. Okay, so because you always talk about the maximum resources that you are going to use. So in this case, the maximum time that you require, or the maximum resources that you are going to use while you are performing this linear search on this particular array, is n. That means you will go through all the elements, and at the end you are able to find out that, okay, worst case makes mistakes. No, it's not about making mistakes. It's about how long does it take in the worst case to find the element. So in the worst case, how many iterations or how many unit operations you're going to perform in order to find that element is big O of n. Okay, that's it. And you always talk about worst cases. You are talking about the resources, the maximum utilization of your resources, what is it, and you're going to talk about that particular scenario. Okay, the worst case is computed always for analysis as it dictates the maximum resources required. Okay, you can say, but yeah, now this n, this can be not large data set, even if it is a small data set, right? If we are talking about 3 elements, again time complexity will remain same, that is big O of n in worst case. If you're talking about 100 elements, that data set is 100, again it will be big O of n. So it doesn't depend on the number of elements that is there, but yes, you can say that it is the maximum number of unit operations that you're going to perform in order to find a particular solution. Okay, done. Now let's talk about our first algorithm that is there, which follows a divide and conquer approach, is binary search. Now what is this binary search? So basically, what do you mean by this divide and conquer? Okay, so basically when you talk about divide, okay, I don't know AI because I'm in class. Okay, so now whenever you talk about this, whenever you talk about divide and conquer algorithms, right, there are three things, right? Divide, conquer, and combine. So you first divide your problem, divide, then you conquer them one by one. We'll see what does this mean, conquering, when you talk about merge and quick sort, what does this mean? Okay, so then you conquer them. That means you are finding out, okay, let's suppose I'm breaking this problem, I'm breaking it, and at one point I'm not able to break it any further. So this is the element that I'm talking about right now. And this element, if you talk about binary or quick, if you talk about merge and quick sort. This cannot be any, we cannot divide it any further. Now this element, we are sorting it, right? So this element in its own is sorted. So we are conquering this element. Now we have conquered it. Now we are going to go backtrack and combine these two elements. So this is what this divide, conquer and combine means. Okay, you guys can, if you have any doubt, guys, just type it in the chat. Okay, so don't worry about anything else. Okay, conquer means, now yeah, is this thing clear, Aditya? So what a conquer means, so basically you are conquering your problem, the sub problem. You have a problem, you divide it into sub problems, right, Aditya? So you divide it into further sub problems, and then you're smaller in when at the end, when you don't have, you can do it recursively or you can do it in a non-recursive manner. Okay, if they are small enough, and then you cannot divide it any further, that means you have reached the base cases. In recursion, you have base cases. When you have reached the base cases, that means you cannot divide it any further, and then you start conquering them. Okay, and then once you have conquered them, then you start merging them. That means you start combining them. Okay, is this thing clear, guys? Quickly confirm in the chat. So you have a problem, you divide it into sub problems with smaller number of instances. That means you are dividing it into further sub problems. Now once you have divided your problem into sub problems, then you start conquering those sub problems. Okay, that's smaller problems, you start conquering them. You start finding the solution for that particular instance. Okay, so conquering means that you're trying to find out that particular, what is the solution. If this would have been the case, if there would have been only that single element, what would have been the result? Okay, now once you have conquered it, then you start combining those conquered elements one by one and start merging them. Okay, cool. Okay, now let's talk about this binary search. Okay, once again, I can't see your chat, guys. Just quickly write a yes or no in the chat. Can't see your chat. Yeah, okay, great. Okay, cool. So now okay, so now let's talk about this binary search. So as we talked about earlier, right, we talked about this linear search wherein we were trying to find this element one by one, right? We had an element 10, let's suppose we are trying to find this element in the array, and one by one we checked all the elements and we were not able to find it, right? But this is this linear search takes much more time to search an element. Is how great it would have been if we would have skipped some part of this array, saying that okay, let's suppose we have this array, and for now let's talk about this binary search in a simplified manner. That let's talk about, we have an array and it is sorted, right? And we want to find 30. Okay, so, or not 30, because we will be able to find it in the first go. Okay, so we are trying to find this 40. Okay, now what we do in this binary search, we somehow divide this array into two parts. What is the time complexity of binary search? Yeah, Aman, we first talk about, let me talk about first binary search, how it follows this divide and conquer paradigm. Okay, and then we will talk about its time and space complexity. Okay, so now what we are trying to do, we are trying to find this 40. Okay, now somehow I have divided this array into two parts. So we have the 0, the starting index, then 1, 2, 3, 4. What we did 0 plus 4 divided by 2 for now. Okay, and we had 2. So we are at this index, right? We find out the middle element and we checked, okay, is this the element that we are trying to find? This is our item that we are trying to find. This is 40. No, it is not. So our array is sorted. Now, does it make any sense to check in this portion if this is 30? No, we know the array is sorted, so there is no point that our element can be on this side. No point, right? Doesn't make any sense. Our array will not be on this, our element will not be on this on this side of the array. That means this is the middle, this is the left part, this is the right part. So left part, there is no point that our element will be on that side, right? So we directly skip these portion, right? We are dividing our array. This is what we mean by divide. We are dividing it. So we keep on dividing it into, so now we have skipped 10 and 20. Now we are talking about these elements 30, 40 and 50. Okay. So now this 30, 40 and 50, this is our mid. So this is not the element, right? Now our starting index is this, our ending index is this. What? This is now our, what we have this as 3, index 3 and 4. Now we again divide it. 3 plus 4 divided by 2, which is 3.5. Truncating the decimal part, it is 3. So now we check, is this the element that we are trying to find? Yes, this is the element. We stop. Even in the worst case, let's talk about the element that is 50, okay, or 60, which is not there, okay. In the worst case, we check, okay, is this 3 the element? Is this 60 that we are trying to find? Is this element 60? No, it is not. What we do, we skip this part as well. We skip this whole array and we talk about this element now. This is our new index, that is 4, and we talk about this. But we have to put a constraint right at the end so that we don't exceed this array, because there is no such element, right? There is no such element, and there is no such element as at index 5 which we can compare it with. Okay, so now let's try to demonstrate it and let's try to find out what a binary search is. You got the intuition that what is it. Okay, so binary search is nothing but a searching algorithm which is used to search an element, right? It is used on a sorted array or an array in which is written in such a manner that you can skip some part of it. Okay, we'll talk about it maybe in the next maybe sometime else. Okay, but for now you can think of it as a array which is sorted, and you need to search an element in that sorted array. Okay, now this is a searching technique which follows divide and conquer strategy. Why? Because we keep on dividing our array into further subproblems, further subproblems, further subproblems, and at the end we conquer that. We try to find out is this the element, and then we merge them. Okay, so this follows a divide and conquer strategy. Okay, this is very efficient technique for searching because we talked about linear search wherein we were checking all the elements, but here somehow we are skipping the half of the array every time. Okay, is this thing clear? So this is it. Okay, so now let's see its iterative algorithm. Okay, so now I told you this is the binary search. It's taking an argument as array and size, the size of the array and the array. Okay, so now let's take an example over here. So we have 1, 2, 3, 4 and 5. Okay, so 0, 1, 2, 3 and 4. So what we are doing, we have this loop condition wherein we are checking that the beginning should always be less than the end. So we check this is our beginning and this is our end. Okay, we are checking, this is the loop condition over here. We are checking that beginning should not be equal to end, or it should be less than what? End. Okay, so beginning is 0, end is 4. We can do this, we can go through this algorithm, we can go through this inside this loop, and we can execute these things. Okay, so what we did, we tried to find out the middle element. Now middle element is nothing but beginning plus end divided by 2, which is 0 plus 4 divided by 2, and we find out the middle element is 2. Then the first thing that we do is that we are checking if that element that is present at this index is the element that we are trying to find. Okay, so we have this item. You can also pass in the item if you haven't declared it globally, or you haven't this is not static. Okay, so you pass in the item as well that you are trying to search. Okay, search. Now what you are doing, you have this item over here, and then you are trying to find out ARR of middle index, that is ARR of 2. So ARR of is 2, and the item that you're trying to search, let's suppose in this case it is 3. Now you see what is the difference between, I didn't understand the worst case. Okay, don't worry Aditya, you will get to know. Just give it yourself some time and you will first let's try to understand the best case of this binary search. So if the element that we are trying to search is 3 and it is present at this particular index, right? 2 is present at this index, and now what we are trying to do, we are trying to find that element itself. So in the first iteration or in the first operation that we perform, we were able to find this. So this is the best case time complexity of binary search, which is big O of 1, which was not the case in linear search. In linear search, this element, when we're trying to find the element 1, this element was the best case in linear search. You see the difference between the best cases of linear search and binary search. Is this thing clear? So we'll start off with the easier ones. These are easier divide and conquer algorithms. We have many complex divide and conquer algorithms. Maybe we will have a session or two on divide and conquer algorithms. Maybe then at that time we will cover this. But for now, is this thing clear? Quickly guys, and just quickly confirm in the chat. Is this thing clear? The difference between the time and the space complexity of what? Of linear search and binary search? Aditya says no. Aditya, what is the confusion? I'm talking about best cases, not the worst cases. So you are dividing your array, right? You're dividing your array and the middle index is at 2, and that is the element that you are trying to search in the best case. Okay, so you were able to find it in the first go, and you see you are returning here. You are returning the index. That means you are returning from this binary search function, and you are able to find this in a single unit operation, that is big O of 1, which was not the case in linear search. You were, if this element was the first element, if you were trying to find this item, then only it would have been big O of 1 in case of in case of linear search. This is the best case of what? Linear search. Okay, now let's talk about the other cases. Okay, so you have 1, 2, 3, 4 and 5. You have 0, 1, 2, 3, 4. This is your beginning, this is your end. Okay, now you're checking. Okay, now you're at this index. Now the element that you're trying to search is 5. Okay, this is your item, and let me name it as item. Okay, so remove size. Okay, so you're checking, is 0 less than 4? Yes, it is, right? And then is you find out the middle, which is this middle index, right? Okay, this is the middle index. Then you're checking if this condition is true. No, this is not true, because we are trying to find 5, which is our item, and the item that we have right now is 3. So we go into the else part. We check if this item is greater than, if this item that we are trying to find, if it is greater than this index. That means if our 5 is greater than 3, so is 5 greater than 3? Yes. So there is no point looking in this portion, right? Does it make sense? You are not going to find this element, no chance, because our array is sorted. There is no point that you will be able to find this 5 on this side, because this is less than the 5. So what you do, you increment your beginning to middle index point plus 1. So your beginning was here, now you have a new beginning, which is middle index plus 1, which is this. This is your new beginning. Okay, is this thing clear, guys? So now, after a single iteration that we just did, we were able to we were able to skip these elements. Now you are only seeing this. What you can say that, okay sir, we are only skipping 3 elements. But what if your array is having 100 elements or 1000 elements? At that time, 500, right, or 10,000, right, 5,000 elements will be skipped in a single go. They will never be checked, because this is the beauty of binary search. In a single go, you are dividing your array in such a way that in a single go, 5,000 elements will never be checked. Okay, now what happens after that? Okay, now we updated our index, right? Let me just remove these things. Okay, now our beginning is here, and this is our new index, and let's remove this, and we are trying to find this item, that is 5. Okay, so this is item. Okay, cool. What is the element? The item is this 5 that we are trying to find. Okay, we are trying to find this item in this array. Okay, so now again we will check, is beginning, that is 3, is this less than 4? Yes, it is. Then what we do beginning plus 3 plus 4 divided by 2, which is 3.5, which is 3. So our middle index is 3. So this is our middle index. Okay, now we check, is this the element that we are looking for? No, this is not. We are looking for 5 and this is 4. Done. We will not execute this block, and then we check, is this 4 less than or is 5 greater than 4? Yes, it is. So skip this element as well. Give us a new beginning. Now our beginning is at this particular index. Okay, now this is our beginning. Okay, now we'll check if this is what I have written in this looping condition. Beginning is not equal to the end. Okay, so beginning should not be greater than end. Okay, so is our beginning greater than end? No, it is equal to. So 4 is equal to 4. Now what we do, we add these things, 4 plus 4, which is divided by 2, which is nothing but 8 divided by 2, which is 4. Okay, so now we check, is this item that we are having, that is this current item, that is 5, is this equal to what is the element at index 4? Yes, it is. So we were able to find this element and we return the index, which is 4. We return this index. Done. This is our binary search. Okay, is this thing clear, guys? So let me just go through the algorithm and this. Okay, so now this is the implementation of the same. Okay, so things will be much clearer now. Okay, so you have this binary search. Okay, this is the algorithm. This is the implementation. We have this input array. Okay, we have this item that we are trying to find. We have this beginning index. We have this ending index. Okay, so this will be 0. This is 4. If we're talking about this array, 1 2 3 4 5. Okay, 0, and this will be 1 2 3 4. Okay, so now let's run this. So this is your beginning, this is your end, and the item that you're trying to find is 5. This is your array, this is your ARR. Okay, clear? So now while beginning is less than or equal to end, yes, beginning is less than end, which means that 0 is less than or equal to 4. It is less than right now. So we check for C++, or Java. Okay, so now is there any confusion in this in this implementation, guys? Any confusion? So you're again, what you're trying to find, the middle. You check, if it is greater than, you increment your beginning. If it is less than, you go on and decrement your end, right? So these are the 3 blocks that are there. Now once the entire thing is over, right, once we have this beginning and this end is at this location and these are not equal, that means you are looking for, let's suppose in this case you are looking for 6. Now you are not able to find that element. Okay, you are not able to find through the entire array, you are not able to find the 6. What you did, obviously this beginning is less than or equal to, in this case 4 is less than or equal to end, right? But now what happens in the next step, since it is not greater than, it's not greater than the item, what we do, we decrement our end. So our end will be here. Now in this case, now our beginning is at 4 but our end is at 3. So we are out of this. Okay, we are out of this loop, and then what we return -1. Is this thing clear for you guys, or do you want me to repeat? Prince says please repeat. Is this the same for all of you guys? Were you able to understand this thing? Quickly guys, just write it in the chat. In the meanwhile, let's try to understand its time complexity. So let's first go into this demonstration. Okay, so you're trying to find this 20. Okay, you have this input array. This is your beginning as at 0, your end is at 4, and you're trying to find what, 20. So you find out mid. This is your mid. You checked, is this 16 equal to 20? No, it is not. Now, but 16 is less than 20, so there is no point you will be able to find this 20 in this portion. Okay, done. You skip it. Going to the next iteration, what you did, you find out the mid. Okay, the mid is nothing. Your beginning is 3 and your beginning is 4. Your end is at 4 because you now these are the updated beginning and ending, right? In the next iteration you are able to find 20 because this is the middle index, that is 20, and our element that we were trying to search is also 20, so you are able to find 20 in 2 iterations. Okay, which would never would have been the case when you're trying to find out in it using linear search, because you have to go one by one and check for the elements. Okay, that would have been the case, and it would have you would have done that in 4 iterations, and here you did it in 2 iterations. Okay, so now let's clear the screen and let's talk about what time complexity. So if you talk about time complexity, what is the value of this log to the base 8? What is the value of this? Can anyone tell me? Any one of you? What is the value of log 8 to the base 2? It can be written, right? It can be written as log 2 to the base 2 raised power 3. Yes, Prince, right? It can be also written as 3 because it is log m raised power n. It can be written as log 2 to the base 2. This log 2 to the base 2 is 1, and this means 3 into 1, which is the value is 3. Okay, so now why I'm saying this thing, if we have an array, right? If we have an array and it contains 8 elements, 0, 1, 2, 3, 4, 5, 6, 7 and 8, right? 2 or 3, why not vibrations, iterations. Okay, iterations. Aditya. Okay, so now what we have, we will be calculating 0 plus 7 divided by 2, which is 3.5. So we will be here. Okay, and we check, is this the element that we are trying to find? No, it is not, right? So we are talking about worst case wherein we have our element over here. Okay, now we are skipping this in the first iteration. Now our new beginning will be here, our ending will be here. Now we again check. We try to find the middle index, which is 4 plus 7 divided by 2, which is 11. 11 divided by 2 is 5.5. We have 5. We are at index 5. We are at this index. We try to find the element. No, it is not. So our beginning will be this. So it will be 6 plus 7 divided by 2, which is 13. 13 divided by 2 is 6.5, which is 6. Okay. Now we are trying to find the element at this location. No. And at the end, we are able to find this. So if you observe carefully, the number of iterations that we did is 3. Okay. In the worst case, when our element is at this location, we were able to find out that element which we are trying to search in 3 iterations or in 3 unit operations. Okay, is this thing clear? So now if the value of 2 to the base n, if we have log n, but here if something is written to the base 2, we have log n to the base 2. Now n is right now it is what, 8, and the iterations that we do is 3. So you can see that what is the relationship. So you can perform this binary search in log n time. Is this thing clear? So this is kind of a mathematical way to prove this. Also you have a expression that you can deal or you can write, right? So every time you're dividing your array, every time you're dividing your array into 2, so it will be 1 by 2, it will be 3 by 4, then 1 by 4, then 1 by 8, 1 by unless and until it is there is only single element, and that expression boils down to nothing but that is a logarithmic expression which boils down to log of n. Okay, is this thing clear? So this is the reason why the time complexity of binary search is bigger of log n to the base 2. Okay, now what about space? Space is constant because you're not using any auxiliary memory. Okay, done. So this is binary search. Now let's see how quicksort works. Okay, and how it follows the paradigm of divide and conquer. Okay, so again it is a sorting algorithm. That means you have an array and you're trying to sort this array. That's it. Okay, now One of the most commonly used algorithm is this quicksort algorithm. Why? Because it follows a divide and conquer paradigm, which is efficient as compared to our traditional sorting algorithms, right? Like bubble sort, selection sort, or insertion sort. Log of n. End, no, not end, Aditya, log of n. Log of n. This is not n to the base 2, okay? So this is the time complexity, okay? So now, what about the rest of the things? Recursion is used in this quicksort algorithm. You are using recursion. Now, unless and until we hit the base case, we are going to divide our sub problems, and we are going to divide our problem into sub problems and sub problems, and then we combine them, okay? At the end, we will have the sorted array. So that is the combined part, okay? So how does this what quicksort works? It works in such a manner that you pick up an element and you make this element as pivot, and based on this element, this is your pivot element. Let's suppose this can be any element, but for simplicity, I'm taking this as the last element in the array. It can be first, but its time complexity depends on which element you are picking, okay? Okay, so now we are picking up this element that is there. This is the last element, and this is our pivot. Now based on this pivot element, we will try to divide our array in such a way, right? We will try to divide our array in such a way that on the left hand side, all the elements from this pivot, this is our pivot, this will have its original position after one iteration. Let's suppose this is 3, then this 3 will be here, and this will be the original position of this 3 when we sort our array. Now listen to me carefully, this is very important. Now this is our pivot, this is 3, and this will be placed after one iteration. This will be placed here in such a way that all the elements on the left hand side of this pivot will be less than, and all the elements that will be present on the right hand side will be greater than. And this will be when we sort this array. If this is at index 2, when we sort this array at index 2, you will have this element in the sorted array as well. Okay, is this thing clear? Is this thing clear, guys? Pivot, you can name it anything, right? But in quicksort, we name this element as pivot because it occupies its correct position in the array, which is supposed to be as it is right in the sorted array. Okay, so with each step our array gets reduced to 2, which leads to quick sorting. Okay, and our pivot can be any element. It can be the last element, first element, or any random element. Okay, so now let's see. So now let's see the quick sort. Okay, therein we have two algorithms, or you can say it is divided into two sections. One is the quick sort algorithm, for that the quick sort, and the other is partition. Okay, so this is our quick sort, and what we do, we always, just like in binary search, always whenever beginning is less than end, we try to divide it further. Okay, then we try to partition it. Now once we partition it, the partition function will be called, and we are passing in the arguments as array and the beginning index and the ending index. Now let's see first this partition algorithm, how it is partitioning it, and then we'll try to see these two portions, because then what we do, we have the left side and then we have the right side. But first, this is our left, this is our right. Let's try to partition it first. Okay, how partition is done. So if you talk about partition algorithm, we set the index, that is the last index, as pivot, right? And we have something that is known as the p index, which is currently at beginning -1, which is at somewhere right here. Okay, now how would you, now our main objective of this partition is that this element that is there, which is pivot, should have, after this partition is done, this element should be at its original position. That is the main focus of this partition algorithm, is that after the entire this partition is done, this element should be at its original position. Okay, is this thing clear? Quickly. Yes, Kashyap, you can say that. Yes, it is the boundary of two lists. Not exactly, but yeah, you can think of it as it is. Okay, so now once this thing is done, after that, what happens? What we do? We check if this index. What we do? We execute this for loop and we start from beginning to n minus one. Okay, we have this beginning and which is n minus 1, this is n minus 1 except this element, and then what we do, we check if arr of I is less than pivot. Okay, if it is, then we swap it, okay, with the next location. Okay, now we check if this is the arr of I, which is this index, this I is over here. Now if this I is less than the pivot, let's talk about this I first. So let's suppose there is an element which is 2, or let me just put it in a demonstration. Okay, so now here you can see the demonstration. Now you have 0 1 2 3 as the indexes, and these are the elements 5 10 9 6 and 7. Okay, now let's try to understand how the partition works. So obviously here beginning is less than 0 is less than 4, then we call the partition and we return the pivot index. Okay, so now here this is the pivot at start, I told you guys, right? Now what happens, we will divide our array in such a way that this 7 is here, right? After first iteration, this 7 will be at its original position, that is this. Okay, this 7 and rest of the elements you see 5 and 10, you see, are replaced. Now you have, with if you have this 7 over here, these are the elements which are less than 7 and these are the elements which are greater than 7. You see the division, the divide approach that is happening over here. Quickly confirm, guys. So quickly confirm just, guys, this 7 is over here and what is happening, this 5 is less than 7, this 6 is less than 7, and you have this 10 which is greater than 7 and 9 which is greater than 7. Now let's go back to this algorithm. Let's clear the screen. Now what is happening, we have this index which is at beginning, right? Okay, 0 1 2 3 4 5 6 and 7. This is 7 index, this is our pivot. Okay, we loop around from beginning to n minus 1, this is our beginning. Okay, and this is our I iterator, and we have something that is p index which is at this location which is currently -1. Okay, now what we are doing, we have this end over here, right? We have this end pointer over here, that means we are looping from this here to here, not the last element. Now we check if arr of I, if this element is less than pivot, this is our pivot. If this is less than, if this is less than, then what we do, we swap arr of I, that is this element, with p index. Okay, now what is happening, p index is currently at -1, so we need to change this from here to here. We first increment our p index, we do the p index over here, that means we are currently at this location, we swap this element with itself. Now why we are doing this, it will make sense. You might be thinking this is a redundant step. No, that is the reason I made explicitly, I am mentioning it here so that you can see the difference, why we are swapping this number with itself. Okay, so now once we are done with this step, the next step is, we are still in this for loop, right? We check the next element. Now let's suppose this element is not less than this element. Let's suppose this was 5 and this was 3. Okay, this element was 3 and this element was 10. Okay, now this element is not less than pivot. Okay, so what we do, we increment our I. So I is here and p index is still here because we just incremented it, right? So this is 10. Now this is, let's suppose this is 2. Okay, this is 2 which is less than pivot. Now what happens, now we are having the p index over here. What we do, we increment our p index to this position because this is less than 2 is less than 5. Then what we do, we swap these positions. This is I and this is p index. So this is what is happening, swapping ARR of I, that is this, and ARR of P index. We swapped them. So now we have 2 over here and 10 over here. And similarly what we have 3 over here. Now P index is at this position. Now let's suppose somehow all the rest of the elements, right? This was 3, this was 10 earlier, this was 5, and not 5, this was 2, and rest of the elements are 11, 12, 13 and 14. Okay, all the elements are greater than. Now once this entire loop is done, okay, we have P index at this position and I would have been over here. Okay, now if I would have been over here, then what we are doing at the end, we are swapping these two indexes at the end. So we are swapping this index, that is this 10, and the last index with this, that means 5 is over here and this 10 will be over here, and rest of the elements are as it is. This is very what you say, this is a very tricky algorithm in terms of how you maintain these things. So you need to reiterate through this again and again in order to understand this. Okay, so you need to understand what is happening. So let me just go here and check, show you guys again in the demonstration what happened. So now what happened, so this is less than pivot, right? It got swapped with itself. This 10 is greater than pivot, it remained over here. This 9 is greater than pivot, it remained over here for now. This 6 is less than pivot. What happened? These two elements got swapped. You see, 6 and 10 got swapped. 6 is over here and 10 is over here. Now once this entire iteration is done, then what we did, we swapped this with this index, because P index was here, P index plus 1, that means this index. We swapped these two elements, that is 9 and 7. So 7 is over here, 9 is over here. So this is what happened after first step. And 7, if you sort this array, 7 this 7 would be exactly at this position in the sorted array as well. Okay, is this thing clear? I know this is getting complicated, this partition thing. Now you have partitioned it. Now what you're doing, you are returning this index. Okay, you see at the end you are returning this P index plus 1. That means you are returning this index, this particular index. Let me just clear it out. Yeah, so you're returning this index, that is 2. Now again what happens, now again if you observe carefully, now we have in the next step we will have a left portion wherein we call this partition again, and the right portion wherein we call this partition again. Okay, so we have beginning, same thing, beginning and pivot. Pivot will be the last element. Beginning and pivot. Pivot will be the last element. So again we sort them in such a manner unless and until beginning is less than end. If beginning is not less than end, we will stop, which will be the case in these two cases. Okay, now after this entire step is done, we will have this sorted array, and these two will be done in just 2 steps. Okay, just 2 steps, your entire array will be sorted. Okay, is this thing clear, guys? I know you need to reiterate through the algorithm again and again. You see, this is the implementation of quick sort. You see, quick sort is over here. You have the array, you have the P index, you have the R, that is the ending index and the beginning index. So beginning index and the ending index. This is your beginning and this is your end. Okay, P and R. So you are checking if P is less than R, that is beginning is less than end. Okay, then you partition, your partition is called, you return one index, and then you call again this quick sort, same thing again, but this time around you call it from 0, that is your beginning, and pivot index minus 1, because pivot index is originally at its own position, it won't change. So you will have this index that is there, and you call the quick sort again on this portion. And in this, what you do, pivot index plus 1, that is Q plus 1. Here you have this Q minus 1. Okay, so you have this partition, that is P index. Okay, so Q minus 1, that means you're talking about Q plus 1 in this portion. You're talking about this element Q plus 1, and the R, that is your end, and you call the quick sort again on this portion. Okay, this is a little bit you might get confused or you might get stuck. This is that kind of an algorithm, and this is very important algorithm to understand divide and conquer strategy, how it is doing this divide and conquer. Okay, so you see, he divided it, you find out the pivot and pivot it at its original position, divide and conquer, done. Divide, then again divide, conquer and combine, divide, conquer and combine. At the end, the combine step will take place, which will be your sorted array. 1 2 3 4 5. Okay, is this thing clear? I'm not going into merge sort. I know it is getting complicated for you guys. So if you see, this is the implementation of quick sort. But what about the partition? Partition is much more simpler. You see partition, then you have this last element as the pivot. You pick the pivot index, which is a pointer which helps you to change or swap these things, swap the indexes, right? So you have pivot index over here, then you loop around it, and then finally the last swap. That's it, done. Okay, and then you finally return the pivot index. Okay, cool. So in this loop, what you do, you just swap around and in such a way that all the elements from this pivot index will be less than, on all the elements that are on the right hand side will be greater than. Okay, okay, cool guys. So I'm concluding this session. If you have any doubts or anything regarding these two divide and conquer algorithms, that is your binary search and your quick sort algorithm, I had a merge sort as well, so that also follows a divide and conquer paradigm. So if you see, let me just show you the image how it works. You see, it works in such a way that you have an algorithm, right, and you start dividing it. Okay, yes, Prince, we have an individual video, that is the recorded session as well, on these sorting algorithms, right? Quick sort, we have a separate video, and therein we are only talking about quick sort. Okay, you can go through that. We have an video on merge sort as well, a separate video wherein we are talking about everything: time complexity, stage complexity, algorithm, implementation, everything, right? Everything is there on our channel. You just subscribe to our channel, that's it. Okay, and plus we have courses available on our channel, that is a 10-hour course, that is data structures and algorithms using C. Okay, you can check that as well. Okay, so you see, if the demonstration over here, we are dividing our algorithm. We have the left part, we are dividing it into two subarrays. We have a left subarray, we have right subarray, then we are further dividing it, then we are further dividing it. This is dividing. Then what happens in the next step? Now we are conquering it. You see, now once we are dividing it, and once you see the image here, we have this division at the last, 0 index and 1 index. You see 23 and 10 at the end. You see over here. Now we cannot divide it any further. Now what is the next step? We start combining it. We start conquering them. Now we have conquered them, we combine them. Now we conquered this, we combine them. Now we conquered this, now we combine them. Okay, this is how your algorithm works. So B-tree algorithm, do you have an implementation of B-tree algorithm? I do have a implementation, but right now I didn't. I was not planning to explain B-tree in this session. Maybe in the next session we can try to write the algorithm as well as implement B-tree. Okay. So cool guys, so thank you so much, and if you haven't subscribed, make sure you subscribe our channel, and have a great day. Okay, thanks a lot guys. If you have any questions, you can post them in the chat. Okay, this is the merge sort demonstration. And if you're looking for individual videos on quick sort, merge sort, insertion sort, we have those available on our YouTube channel. Plus we have a separate course, that is a 10-hour course on data structures and algorithms. Plus JavaScript is also there. Data science is also there on our channel. Okay, all these things are available on our channel. Okay, thank you so much guys, and this is it from this session. I will see you in the next. Thank you.